So we've organized some of the questions from the Slido app to get the highest voted ones. And to start, I've picked a pretty broad question that I'm hoping we can get everybody's input on, and we'll go in the speaker order. So, so the question is, if you had to pick one research topic that you feel is underdeveloped and needs more people and ideas and hours devoted to it, what would that topic be? Elizabeth, could you start answering that one?
I don't want to have to pick one. I don't think I've ever worked in the field that way. There are so many topics that will benefit from more work, especially more interdisciplinary work, I think. Connecting developmental psychology to machine learning and artificial intelligence. So sorry, can't do it.
Okay, yeah, that's allowed. Aude, do you have another answer?
So the topic for me varies every year because it depends on what I know and what I'm excited next. So certainly I feel that both in computer vision and machine learning in general, we should attack analogy. We should start working on a question that require analogy in language or vision in order to be solved, because it's a long way ahead. So we need more power there.
Yeah, that sounds great. Analogical reasoning doesn't have much work in it right now, I think. Dan, do you have a topic that you could pick?
Well, obviously, you know, the functional use of language is close to my heart, but I would say, I think maybe the most interesting scientific topic is that we don't have a theory of change that's not kind of optimization-driven learning. And presumably some of what we think about as changing in children and adults over time is that, but some of it probably isn't. Like, you probably don't get taller because you're trying to optimize reaching tall stuff. And it would be interesting to know, to have a theory of change that's independent of trying to solve some proximal optimization question, and then to understand if such a theory would be relevant for machine learning as well.
Yeah, that would be interesting. Remote, we had Josh, but he's gone again. So that means, Linda, we go to you. Do you have a topic that you feel needs more work hours put into it? Yeah, Linda, sorry, but you're muted right now.
Yep, I know. I didn't hear you, so all right. So a little bit, I believe, like Liz, that it's not probably all that wise to pick one topic, and I think the things that have been raised are actually pretty good. But I do believe that I think we need a theory of environments, and this doesn't mean simply because they might change everything we do, but if one really wanted to put agents into the world, I think that we have a very warped sense of the massive, sparse, temporal properties, spatial properties of the world, and that we really don't know what we're trying to build something to succeed in at all.
Okay.
So a theory of the environment or environments.
Yeah, that sounds challenging. Bruno, what is your topic of choice?
Yeah, I think maybe close to that. I think it'd be the problem of how you build a three-dimensional model of the world. And like Jitendra pointed out, you know, SLAM is very much a solved problem, but it just delivers you a point cloud, a 3D point cloud, and that's not what we want really. So how do we build a three-dimensional model that has the information we need to interact with the environment, some kind of a surface representation, and how do we build that in a way that's stable? So what's the other remarkable property is that despite the fact that our sensor input is highly dynamic, very unstable, like Jitendra showed that movie of walking through the grocery market, your head is moving around, your eyes are moving around, it's a foveated image, it's highly distorted. We have this very stable perception of the world, experience of the world. And so how do we do that neuronally? I mean, it's like a complete disconnect between everything we know about the sensory input and things we know in neuroscience about the internal representations in the brain. And so that to me is a huge mystery, interesting computational problem.
Larry, this question is pretty closely related to your whole talk, actually.
I think basically a topic that would push the deep learning community back on their heels, I think would be great. Specifically, it'd be interesting to think about a simulation environment where the metric is not just how well you perform on the environment, but how well you perform in that environment given a limited budget of interaction. So if we could come up with a nice interactive environment that was rich, and we allowed the AIs to basically only exist within that environment for a finite amount of time, which is relatively short, not deep learning amount of times, not like millions or billions of examples. And then had it show that it generalized well, or that it could do well beyond that. I think that would push people in thinking about problems in a different way. And the trick is how to take a problem like that and make it something that people are genuinely interested in, and the community kind of becomes engaged in, and it's not just like a fringe.
Yeah, it's difficult to engage a whole community, I suppose. Allison, do you have an answer for this?
Yeah, I mean, I think there's sort of some more proximate answers and some that are sort of further out, the way that is often the case. So I would echo what Ode said about analogy. That's something that a lot of people have talked about, but we don't have very good formal models for. We don't even have terribly good empirical evidence for. But one of the things that we're doing in my lab is showing that even very young children are doing something that looks like analogical reasoning and using it to solve these kind of conceptual problems. Another more proximal one is the search problem, right? So I think very often what happens is we have good ways of representing something about our knowledge or our understanding of space, of space or of objects. But if we consider the range of possibilities that we can get to, how we search through that space in some reasonable way, I think that's turned out to be the thing that's really, really deeply challenging, and how much of that search involves a certain amount of stochasticity and how much of it involves some kind of directed search. I think that's very much something that's up for grabs. But let me end by saying something that I think is really much further out, but I've gotten interested in, which is, what role does care play in all of this? So we started talking about some affect like curiosity, but one of the things that's really striking about human beings is that we have these care relationships, particularly children. So it's not just that children are growing up and having these caregivers who, keep them alive, or even these caregivers who give them some data about the world. There's something special about that relationship of care. And one way that I've been thinking about it recently is care actually enables you to design new objective functions. What we do when we're caring for another person is figuring out a way of allowing them the autonomy to develop their own objective functions and have them be fairly reasonable new objective functions. And I think that question, how is it that we can manage to say, get a new generation, is actually very relevant on this particular day. How could we get a new generation that decides that their values and rewards is different from a previous generation, and what role do these kind of caring and attachment relationships play in that? That's something that I think is kind of further out, but something that would be very helpful to figure out. How can you develop a new objective function that's different from the objective function that you started out with, and how do your social relationships play a role in that?
Jitendra, can you comment on that, or choose another topic of high priority?
I think I believe in Peter Medower's heuristic, which is that research is the art of the soluble. So to some extent, you have to pick problems for which the technology, the data, the ideas are sort of aligned so that one can make progress. From that perspective, I think spatial intelligence to me seems ripe, in the sense that it's important. We have made some progress. We have some of the tools like simulation environments and so forth. So, so problems like navigation and so on, I think we can make good progress on manipulation. I think what I'm frustrated by and I want to make progress on, but have not had much luck, is this kind of common sense reasoning of human behavior, right? So understanding human behavior from like what classically people would call schemas and scripts and so forth. And how do we acquire these common sense models? I mean, Odd knows years ago, we were working on a grant proposal together, and I still feel that, like, at least for me, I feel that this is a great problem, but I don't have not made much headway on it. Maybe some bright kid in the audience right now will figure it out.
Yeah, hopefully. Josh, we skipped over you, but the question on the table right now is, if you could pick one topic to devote more resources towards, what would that be?
Yeah, and I hope it's still working. I think all the suggestions people made so far were great ones. Resonate a lot with my thinking. Maybe I'll just amplify on one or two of them. So the thing that Larry said about the challenge of an environment for an agent to learn has very little experience. I mean, I guess, yes, fundamentally, I said where wants to encouraged or forced to learn in more, so goes along with that with our visual system real world, and yet we can generalize instantly with no retraining to any number of different video games or Minecraft or pixels or dots or so many different ways of seeing objects and agents. We can generalize to viewpoints. Like, think about the first time you took an airplane trip. Probably many people may not remember it. Some people may remember the first time they rose up in an airplane. It's surprising what the world looks like from above, and yet you can still make sense of it. Right? Oh, that's what you didn't know that's what trees look like from above, but you know what the trees are, right? And the houses and the cars and the people. So having challenges like that, especially if we're going to talk about resources where you're developing some kind of challenge domains, call it cross simulator transfer, like radical transfer together with radical sample efficient learning would be important. But as far as a challenge, a thing that I think we're making some small steps of progress on, but need a lot more work on. The thing I was talking about at the end of the talk, and it relates to like the search problem as Allison talks about it, which is just, call it structure learning or learning programs or learning code, the kind of learning that isn't just tuning parameters in existing functions, but writing new code in some form. If we really want to think about common sense knowledge and how we go beyond the very earliest stages of what's built in, I think that's going to be important, especially if we want to understand what happens when language comes into the picture, and how does language qualitatively extend our common sense into domains that are not part of our core endowment, are not shared with amazing jumping spiders or ninja squirrels.
Part of the difficulty here seems to be that we're entering more and more into these research areas that are less easily defined in quantitative terms. I think, Jitendra, you said a version of this when you said that science is the art of the soluble. I suppose that's a quote you got from somewhere else. And Larry, you mentioned the same thing when you asked, how do we publish a paper on something that is hard to quantify? So maybe, Larry, can you talk about that a little bit more, and we can try to get answers from other people on the panel?
Yeah, I mean, I guess one of the problems is when we think about common sense knowledge, and a lot of times we think about interaction, and we think about interaction with humans, and we think about how do we quantify those interactions. Dialogue's a really big one. How is a dialogue successful? How do you evaluate whether a bot is good at conversing with another human? Can you do that without actually having a human in the loop? Like, that's really hard. And I think it's one of the reasons why we see research in dialogue as being one of the more challenging areas, because it is hard to quantify whether a bot does well in that scenario or not. And I think there's a lot of other scenarios like that. And I think we'd see a lot more work on common sense if we could do more research on interaction and not just discussing, not just talking, but in actually helping humans do different tasks. But I think we're not doing that because of the quantifiable, because it's too hard to evaluate. And it's hard to write papers on it. And I think that's one of our blind spots there. That it's good when you see it problem, which pops up a lot, when we start talking about this space.
Linda, are you trying to say something? Yeah. Please go ahead.
So I really liked everything that Larry said, and I'm a big believer in doability. In some sense, the best next step in research is the best local decision, and in some sense, what you can do. But I understand the value of benchmarks and evaluation and what role they've played in the advances in computer science. But in many cases, it seems to me, again, I'm just a developmental psychologist here, but it seems to me that some of the definitions of the benchmarks are way off what you want to do, and that they may be deeply distorting or delaying theoretical advances in terms of kinds of approaches. It's exactly your example of writing labels onto scenes, or just beating, classification of ImageNet or ObjectNet by a few percentage points and in some way that, it's like all this work, and maybe the question, maybe the task you're giving or the way you've defined it isn't actually right. And so certainly you need benchmarks, but to rush too quickly to an evaluation scheme when you don't actually know what you want to achieve, a little Wild West might do you good. That's what I want to say.
Like as a community from like computer vision and developmental psychology, I want to ask you guys, like, what should be the best way for us to like collaborate together and then come up with this evaluation, or a way to design the evaluation? I mean, right now we have things like Animal Olympics, and we also have the DARPA also supports some of the evaluation, but it still seems like unsatisfied. So what is missing there? What should we work on to get this evaluation done properly? Oh, so just raise your hand or unmute yourself if you want to say something.
Coming up with good evaluations is really hard, because you have to, it's like what Jitendra already mentioned about research, small steps of what you want, is you have to hit the community just at the right time. Like right when, that task is just barely within reach, and it's compelling to the community. So you have to kind of aim it in the right direction and have it just graspable. The problem with that, though, is I think, in Linda, what you were saying is that can feel very unsatisfying, because really what you want is something that's over here or something that's beyond reach. And it doesn't feel in the short term that we're getting anywhere. It's only over, the really long term that you really see a direction going. As far as how to work together, I think it's about communities understanding each other better. And personally, I can't comment on that as much, because I don't, to be frank with you, I don't think I understand your community quite as well as I should, in order to be able to come up with what is the right task.
Well, here's one thing that we've started to do that I think might be helpful, which is, again, I mentioned this in passing about thinking about VR, but you don't even necessarily need VR to be able to have environments where you could directly compare, say, children and AI agents. So I talked about this in my other CVPR talk. I'm thinking I should have done it in this one as well. This is the work that we're doing with Eliza and Pulkit, where we have the DeepMind lab from Google, and we figured out an interface so that we can actually have children engaged in DeepMind lab, literally in the same environment, doing the same things, solving the same kinds of problems as the AI systems are doing. And in fact, we're doing a collaboration now with DeepMind where we're setting up assorted exploration algorithms, for example, so we can actually have as a sort of benchmark, here's this one set of mazes that you have to get through, here's what real children do when they're trying to make their way through these mazes and solve this navigation problem. And here's what, and any number of different exploration algorithms can go through exactly the same maze in exactly the same environment, and we can see what they're doing. And again, in that other talk, I talked about how we're starting to do comparisons between what the different RL agents do, what their strengths and weaknesses are, where they get stuck, how good they are at actually doing that exploration. And we're doing a similar project with Google Brain, where we're looking at some of the robotics environments. This is echoing what Jitendra was saying about doing social learning, where we have the people at Deep Brain are training robots by having them see human beings in a virtual environment manipulating objects. And then because it's a virtual environment, the virtual robot can literally be manipulating the same objects and doing the same kinds of things, and then using the data from the adults to try to figure out how to perform the actions themselves. Now, of course, getting them out of the simulation and into the real world is another set of issues. But I think if we could kind of have comparable environments that we could actually have children involved in, and that we could have AIs involved in, that's one way. Another thing is, though, kind of, again, I mentioned the work that Linda's doing, where what we could do is take the, Jitendra mentioned these first-person data sets from adults, but of course adults are, complicated. They're doing lots of things. If you had that first-person data set for me wandering around Berkeley, a lot of times it would just look as if I was completely randomly wandering around because I was thinking about something else and bumping into things and getting lost. But we could take some of the data from kids, from babies, which we now have through things like head-mounted cameras, and actually see what happens if you run deep learning, different kinds of algorithms on that data. So that would be a way of having some of the advantages of the benchmark, where it's not quite that you're just going off and doing your own thing and looking at your own, looking at your own set of problems with your own set of techniques, but we could also have some interaction between what we're doing with the humans and particularly with the children, and we could test a whole bunch of different systems and test humans in what are actually the same environments. So one thing, for instance, that we have been we were getting organized to do is what happens, for instance, if you put either an agent or a human in an environment that violates the laws of intuitive physics. What do they do? What kinds of, who's better or worse at dealing with a situation that doesn't fit the actual world that you're in, but has some other set of regularities, for example? That's a kind of interesting generalization task. Sorry, I've gone on for a while, but I think that idea of trying to design environments that both humans and artificial agents could be in at the same time, and you could record what both sets are doing, would be one way of both having the interaction and having a kind of set of benchmarks.
I see. So yeah, that is interesting. So I'm wondering, like, on the computer vision or computer science side, we build so many simulators. We build like AI habitats. We build different kind of evaluation system. What is still missing there in the evaluation system? So it seems to me right now, maybe like in AI habitat, it's about navigation, but here we want to incorporate more tasks that is relevant to babies. So what kind of task can we do it in the, maybe like say AI habitat or other simulator? Jitendra, maybe you can take this since you're
so I think in Habitat, we're going in the direction of making it possible to do more interactions. So have objects which can be moved around and so on and so forth. So that's the direction in which we are going. So, I mean, navigation in a sense is like a success story. We have been able to do a lot of good research on navigation using these simulation environments. But if you look at the field of manipulation, right, robotics, I mean, I think they are in trouble, right? I mean, they might disagree, but that's at least what I think. And I think that if we could create environments in which one could manipulate objects, I think that would be useful. Now, there are environments like AI to Thor where you can do some manipulation of objects, but the physics is a little bit magic physics, right? You come near to an object and then the door opens up. It's like open sesame kind of stuff. So maybe we need a bit more realism than that. There's always a choice with simulations of how realistic do you want to make them? And the answer to that is the one from Box. All models are wrong, but some models are useful. So all simulations are wrong, but some simulations are useful.
Should we make our efforts into making more realistic physics engine, or should we focus on like creating more tasks, like not just like pick and place?
Both. I think that there are plenty of tasks where it's not the realism in physics that is holding us back. I think that is true. It also is worthwhile to improve the quality of the physics simulation, and that for me is really a call to the computer graphics community, because those folks have been spending way too much of their time trying to keep Hollywood happy. Instead of keeping Hollywood happy by generating visual effects, if they instead worked with us on better simulators, we would be happy and they would feel a greater sense of reward.
And we would pay them just as much as Hollywood, right?
Actually, they don't. Hollywood doesn't pay them that much. Hollywood is actually their skinflints, in fact. I mean, this is surprising because Hollywood makes lots of money, but the people who do visual effects don't make so much money. So, and I meant the reward in, it was meant to be a play on a reward for RL, yeah.
Here's a suggestion that has occurred to me, which is tool use is a domain that might be an interesting domain, both from the computational point of view, certainly from the robotics point of view, from the evolutionary point of view, from the developmental point of view. There's a bunch of different literatures about how we use tools and how we use tools effectively, but they're very scattered. They don't interact very much. And that's the sort of problem that, isn't a great, it's a very concrete problem. It's a very useful problem to actually be able to use the right tools to accomplish ends. It's something that you would want, a household robot to be able to do. But it's also quite sophisticated, and it's something that very young children are already doing. But it's quite sophisticated, and we don't quite know how it is that we manage to do it. So a simulation environment where you could pick up tools, design them, figure out how to use them, seems like it might be helpful.
Yeah, that's plausible.
Linda,
I'm not sure. I'm not sure if all of you saw my talk on this, but this is one thing that I talked briefly about towards the end, what we call the virtual tools game that Kelsey Allen and Kevin Smith have done. And Facebook has the Fire Challenge, which are both kinds of tool use things. I know that inside Google, like Igor Mordash and others are working on things like that inside Google Brain. And actually, some of us are putting together a NeurIPS workshop proposal on this topic. So actually, if anybody's interested in that, let me know and I'll put you in contact with the real organizers behind that. Because I think, just as Allison said, like, tool use is a great place where perception and some kind of common sense reasoning, both intuitive physics and understanding of object kinds, goes together with planning. It's at the heart of human intelligence, going back, to our evolutionary roots, yet also shared with, in some form, with some other animals. That's a great challenge area, and it might be, as Larry was saying, right? This might well be one that is not, that there's part of it at least that the community is sort of ready to make progress on, and there's other parts that are further. I would just say, I sympathize with both. Just going back to the other question, also, I sympathize with both the short term. We need something that the community is ready to make progress on, but also we need to set our ambitions high because we're so far from the final goal. So this is also why I think it's valuable to talk about not just a single challenge, but like a landscape or a spectrum of challenges that can get more difficult as the community catches up. I think some of us look to cognitive development that way because we see, well, if we could try to build a 3-month-old style intelligence, that would be easier and is closer to what we can do now than, a 6-month or a 9-month or a 12-month or an 18-month and so on. And that's at least one scaling path that we could start to follow. There are others. And so I would encourage people to think that way, but also then people have to recognize and be patient and not feel like, sometimes I've gotten into this dynamic, and I've seen this where somebody like from cognitive science or something, or sets a challenge, and then somebody meets that challenge or meets part of it, and then you set a new challenge and they say, oh, you're moving the goalposts on us now, right? We have to say it's not about that. It's actually, yes, we're doing that because the ultimate goal is really far, but we have to set up a series of near-term goalposts that people can reasonably aim for. And we all have, as a community, have to work together on a whole path of goalposts that will take us ultimately towards where we want to go.
So we need a challenge curriculum.
Yes, it's kind of like, exactly, that's a good metaphor or a good analogy. Yes, but yeah. But, you know, again, the field of cognitive development, though, there's still so many things we don't know. That's one of the reasons why it could be appealing, is to look to it as actually a whole challenge curriculum.
Yeah.
Oh, Linda, please go ahead.
So I just, listening to this, and I just want to remind how much we don't know for going into simulated environments, okay? No one would think natural language processing would not be where it was if we didn't know what the structure of language was in terms of its frequency, distributional, and cluster structure. So how are you going to simulate this environment? When we're looking at the home view images of babies, we've been very interested of late in people reaching for things and causal actions, because we know that babies certainly by 8 months have really good understanding of how hands work, okay? Well, I mean, there's all kinds of questions that are interesting there. What are the trajectories? How noisy are they? What are the regularities, okay? And it is not what you might do in a simulated environment and what the structure actually is in the world. So when I say a theory of environments, I really mean a kind of mathematical, computational theory. How noisy, how specific, how general, how much do the laws of physics get violated? Do the little feathers not actually drop down but float up, okay? The real world is a complicated place, and physics are complicated in the real world, okay? They aren't quite perfect because of, you know, the engineering side of things, a lot of things that interact. And I think that, I don't know, I'm not overwhelmed by the idea of making perfect little worlds when we have no idea what the structure of the world is for the things that we matter. It really would be like trying to, you know, natural language processing wouldn't have happened without Chomsky, without some deep understanding of what the structure of language was. We have no understanding of the structure of environments at all. Just a thought.
Well, maybe I'll respond to that. I think, I mean, this is always about successive approximations. So I think if we look at the history of AI, it's littered with, sometimes you make approximations which turn out to be very bad. So the blocks world, going back to AI of the 60s and 70s, that didn't turn out to be so useful. But then there are toy problems like digit recognition, which turned out to be quite useful in the sense that it put us on the right track. So it's a little bit like you have to just try things out. And the principle that we have been using is that I want to avoid video game environments. I want to have environments which are captures of reality. Now, so it's real houses, real apartments, real rooms. Do they have the clutter corresponding to what a toddler has in terms of the objects within the reach of a toddler? No, probably we got that. We probably can't claim that level. But it might be good in terms of an adult. Now, we might land up hitting on good models, or we might land up, this model may be wrong in some very essential ways. It could be, but we'll figure it out after getting started. Sometimes it's important to get started, because if we, in my experience, I've been in the dataset game for like 20 years. And when you start, anything you do is going to be critiqued, and it just feels like, oh man, what's the value of this? But we have to start, and then it gets better over time. I think that's been the history of our field.
Larry, you have a comment?
Yeah, just to counter Jitendra there a little bit. I actually think there's a lot of value in video games and more abstract environments. I think one of the problems we have is getting bogged down by a lot of the low-level vision tasks that are involved in realistic environments and understanding realistic environments, mapping them out, etc. Where when we think about common sense reasoning, a lot of it is more higher level. You know, how to learn from a few examples, how to generalize, etc., which I think can be well explored. And I think Josh, you know, he done a lot of great work in this space in building, more simulated environments to really kind of just focus in on that one aspect. And I think given that that's a area that there's a lot of uncertainty in right now and a lot of research that needs to be done, I think it's good to kind of focus on that area, for this domain.
Yeah, can I just extend on that? Look, I love vision. Some of the first work I've done in the field was in vision. The first conference I ever went to was CVPR in Seattle in 1994. And I'm really glad to be back at CVPR. I just wish it was in Seattle. But I also, and a lot of the work in our group is basically vision. But yet, just like Larry's saying, there is a deep modularity here between common sense and vision. Vision may be, for most of us human beings, our most, best way to access the world and to get the common sense representations kind of calibrated to our environment, but it's not the only way. And there really is real modularity there. You can see this by closing your eyes or turning out the lights, or the power fails, or if you lose your vision, you still have your common sense. People grow up all the time never having seen in their entire life, and their basic common sense is remarkably the same. There are small differences, but it's remarkably the same. I remember Jitendra, we participated in that NeurIPS workshop, I think it was 2003. It was the first human level AI one. And we debated these things, and we talked about Helen Keller, and we talked about video games, which weren't nearly as good then. We've been having these debates for a while. And, again, I love vision. This is not a knock on vision or how much vision is important to the broad program of common sense. And yet it really does feel like we can modularize these two parts of the problem. We can ask, one, how do we go from image sequences to the basic stuff of common sense representations? And then separate from that, once we have them, once we have objects and people and 3D, then how do we learn about that? How do we reason? How do we plan? How do we explore? So having, multiple kinds of challenges, including ones which have, really realistic or real perceptual data and all the complexities of that, but also having the ones that, video games or other kinds of simulators can give us, I think we need both of those.
This actually reminds me of Elizabeth's talk in the morning. So you talk about baby recognize the space, not just based on the pattern on the walls. So maybe you can suggest us something more than vision we should add in the simulator or our evaluation.
Well, for sure. I mean, for space, there's moving around there, and the representations guiding navigation go way beyond vision. Though, as I said this morning, they also depend on it, especially when we're using the environment to correct our sense of where we are as we're moving through space and to maintain our orientation. But actually, as everybody was talking, and especially Linda, when you were talking about how little we understand about the environment, one thing I wanted to add there that I think we need in order to understand common sense is we need to think harder about the social environment, because I think that actually from very, very early on, you showed, Linda, that faces are a huge part of what babies are looking at. They're also a huge part of what they choose to look at when they've got different options of which way to turn, what to explore, especially early on. And then actually once kids start learning enough of their language that they can use language to be communicating with other people become a fabulously important source of information about the world for them. And I think it may, as your community progresses in using better and better simulations of natural environments, I think there's going to be a real challenge of figuring out how to capture the social side of learning, which I think is very, very important for cultural learning of kids. I also think it's really important for children's abilities to form new concepts and whole new systems of knowledge. Children may have the capacity to do this on their own, but the chance that they would hit on anything that would actually turn out to be useful, if this process wasn't taking place in interaction with other people who are older, who've already found some of the useful concepts out there that Darwin didn't give us, but that people we use in our thinking all the time, in our common sense reasoning. I think we're going to need to get a better grasp of social cognition, and that's a whole field. I didn't even really mention it today in my talk, but there's tons and tons of work, starting with very young infants and progressing through development, looking at children's understanding of other people, the inferences they make about their mental states, about their actions and the actions that they learn from them and so forth. So I think that's going to actually be a big challenge for making progress on, especially understanding the ways in which we depart from other animals and depart from the simple, relatively simple kinds of abilities, hard for us to understand, but still in this context, relatively simple abilities to navigate through the environment, interact with inanimate objects and so forth. Everything gets way more complicated, but also way more opportunities open up, I think, when we look at the social side of cognitive development.
Cool. So actually, so just I guess like over the course of today's talk, you guys, like especially like all these people from developmental psychology side show that babies are actually great at like so many different aspects when they're like in such a young age. So my question actually goes to like you know, learning from toddler versus adult says something about like orders of learning. But among all the things that baby can do from a really young age, you know, like social interaction or like even sensing space, depth, like which one do you think it's like accidental, but you know, just kind of happen because they need it, or which one of them you think that has very significant benefits for later learning that, you know, we training AI systems should really adapt so that we, you know, the system in the later on stage can like grow better and, you know, have a better ability to generalize. Maybe I can also have Elizabeth to answer first. Oh, you're muted.
I seem to be hit with the questions of pick out the one thing that that would be most useful. Then I feel like I'm really bad at doing that. I see just so many areas where there are challenges that I think we can make progress on. So I want to, again, let somebody else who has an idea for one thing to come forward with it.
I guess doesn't have to be one thing, but like what is the thing that, you know, baby knows to do that we absolutely need to put into the AI system right now? But you know, a lot of things could just happen, right? Like it doesn't necessarily like tell us that, like, you know, we don't want AI system that mimics everything that babiys do.
Okay, then let me
comparison is helpful
against that question. I think there was a long tradition in psychology of actually this goes back to Piaget, of thinking that there's that there's a unity to an infant's mind. There is one basic fundamental cognitive ability that will explain everything, and we can look at children's developing concepts in any different domain, and it will all be rooted in assimilation and accommodation or something like that. I mean, the particular notions have changed over history, but there is that idea about human minds, and I think that idea is fundamentally wrong, that there are multiple systems that come together to make a human mind, not simply one. And that we need to understand all of them, and our common sense builds on all of them. One of the reasons why I think we have the intuition, perhaps, that our minds are unitary is that once we start using symbols like language and and spatial symbols and systems like that, we're able to combine information that has come from diverse sources in new ways, and it looks like we have this seamless web of knowledge. But underneath, I think there are important distinctive systems for representing where we are in space, for representing objects and how they behave, for representing other people and as sources of information for us, but also as entities on their own that are interesting in their own right, that we try to engage with and understand. And these aren't going to all reduce to one problem. And I think we need to have a focus on multiple distinct capacities and how they come together over development if we want to develop human-like common sense.
I'd have a rather different answer, which is, you know, one thing that I mean, I think that's true, but I also think one interesting kind of strategy is to think that a lot of the things that look like bugs in childhood cognition might actually be features, that things like things, so if you're thinking about it from an AI perspective, a lot of the things that look like noisiness, like bad executive function, like all the things that kids are not very good at doing, being bad at maximizing rewards, that all those things might actually be features from the perspective of other kinds of objectives, like trying to extract as much information as you can get from the world. And I think the idea about thinking about intelligence as involving a kind of trade-off between different functions rather than being, this is also echoing what Liz said, rather than being this kind of unitary process, I think development can really help you to see that. So the kinds of things you need to do to extract information from the environment might not just be different from it, they might actually be in opposition to the things that you need to do to exploit, to be able to have goal-directed behavior. Or if you think about some of the ideas that people like Tom Griffiths have about resource rationality, the kinds of things that you need to do to be able to do something swiftly and effectively and with little computational resources might be really different from the things that you need to do when you have lots of computational resources that are available to you for a problem. So I think some of those ideas about trade-offs and the ideas that things that look like they're really bugs about children might turn out to be features, might be a good strategy for AI to use. It's also interesting that, if you even just look at neural development, after all, neural networks are supposed to be sort of the model for what goes on in lots of machine learning. But when you look at actual development, what you see is not that there's a single unitary process by which more and more connections are being formed, for example. There's some real discontinuities where you'll see one process early on, like lots and lots of neural connections, and then you'll see a period of pruning, and that can even be different for different parts of the brain at different times. And again, not thinking of it as necessarily there's a particular optimization function that you start out with when you get your first piece of data, and then you just continue with until you've got the answer. That doesn't seem to be the way biological systems work, and it certainly doesn't seem to be the way that children work.
I actually really agree with what you just said. I guess that's also why I asked that question, because since what in maybe another way to ask the same question is that, like, among all the bugs, which kinds of the bugs, or which bugs are the one that we should actually try to replicate first, and then maybe and then we can change the learning goal along the course of learning, and then maybe the model would in the end demonstrate a better way to generalize. But adding the I guess the loss function to mimic those bugs is very intentional, and that's why I feel like kind of choices here are kind of there's more degrees of freedom here that for us with new models.
Can I?
Yeah.
So I guess echoing and amplifying some of the things that both Liz and Allison said, but I don't know, maybe pushing back against this framing of bugs. Like, it's hard to say we're going to motivate a lot of engineers to build AI by trying to incorporate what we think are as the bugs of humans. But another way to put it is things that we might have thought were bugs are maybe just about a different loss function, and trying to understand the space of loss functions, which is huge and really interestingly diverse. Again, I think this is another way to put some of the things that Liz and both Allison were saying. And in the talk that I gave at the end, when I talked about this idea of the child as hacker, when you think about, I emphasized all the different ways and kind of practices of modifying code. But think about when we're working on code, all the different kinds of loss functions that we might adopt. One of which is maybe the standard one in machine learning, which is accuracy on some data set. Sometimes our code, predicts something, and we try to tune parameters or modify it to make its predictions more accurate. But we talk in our paper, we talk about being, code could be more concise. It could be easier to understand. It could be faster. It could be more energy efficient. It could be more new. It could be more modular. It could be more general. It could be more robust. It could be more elegant. It could be more clever or fun or easily understandable. These are all things that we know, that's just some of the loss functions that we have when we're, say, writing code. And you could think of children's learning as also, in different times and different places, moving between these many different kinds of goals, ways to improve what we know, or how we think. And it's many different things we could mean by improve. And somehow, maybe through adopting these and many other possible goals for thinking and learning, that might take us to places that just trying to optimize for, say, accuracy on data set, even with sample efficiency and even with the right simulator, it's a whole other space of thinking about cognitive development that could be valuable for us.
Okay, I want to come in here because I actually like the way Allison said it better. Okay, but I would use a different word. You talked about all these things that sounded like they were there in some teleological way to know what task they want to solve. Some of these are immaturities, but they're immaturities that are in the system, okay, in ways that are probably extraordinarily helpful. The fact that young babies,
no disagreement there. Yeah.
you know, the fact that they are perseverative is probably a way to master tasks like getting cups on top of cups. They just pound over and up. They are perseverative. Okay, and we think of that as bad. And if you do it as an adult, you look like something's functionally wrong with your brain. But it's a good immaturity. Okay. The bad vision of young babies is probably actually doing in that first 3 months is probably doing a good job for them in finding contours worth findings and movements worth seeing and other things. I mean, I think that these are immaturities, and they are kind of bugs. They're little oddities, but they actually are a set of oddities that get the system off in a perhaps.
But I mean, do they have to be? I mean, the immaturities or constraints or limitations or, you know, but I guess I think of bugs differently, but I mean, no disagreement with the substance of what you're saying, or maybe I just like the word immaturity better than bug. But.
Yeah, the point is that they're not bugs, they're features, but they might look like bugs if you were thinking about them. And I think this is Linda's point in comparison with the adult system. So if you had a kind of teleological vision where you said, oh, look, you know, their vision isn't as good as grown-up vision, or their executive function isn't as good as grown-up function. This is what I think of as a sort of childish defective adult model. Then a lot of those things might actually look like they were bugs. And the point about this for the AI people is that the fact that the systems that we know of that are the most intelligent or designed this way might be a cue to the fact that actually there's some relationship, maybe not a teleological one, but there's some relationship between the fact that you see these limitations early on and then you see this system that becomes incredibly intelligent. And, you know, strikingly, we are more immature for longer than, say, other animals are. So there does seem to be something, even though this immaturity is so costly, we have to put so much work into keeping those children alive. There seems to be something about that kind of strategy that's true. There are some things that aren't just limitations, though. Like, so if you think about the motivational system for exploration and curiosity, you know, that gets kids into lots of trouble. And in that sense, it is a limitation, but it actually leads to more variability, more stuff, more information than you would get to otherwise. I would just echo what Linda said. I went quickly through this, but in the experiment that I talked about, the reinforcement learning experiment, part of what's sort of striking when you're watching it is here's this little kid and they put the block on and then you take away the stickers and they're really crestfallen, like, oh no, I lost the stickers again. But like, I just can't keep myself from putting the block on and seeing what's going to happen. So that's a really active, that's an active motivational system that looks irrational in some sense, but may not be in terms of this broader developmental, the broader developmental sense.
If I could jump in, there's a little remark to be made about culture or scientific culture, right? Many of the people who come into computer vision or machine learning, they come from sort of a mathematical discipline, and there's this mindset which is very reductionist and parsimonious. I mean, economists are the same way. So what you do is you try to make it very simple, just have two terms in the loss function, or ideally one is even better. And that is often at odds with the richness of the phenomena. And but oftentimes some of the debates which happen are to do with that, because they're just coming from different aesthetic considerations. Because for those of you who are experimental scientists in development, I mean, the phenomena, they are God, right? You have to pay attention to them. But for a computer vision researcher or machine learning researcher, they are merely suggestions, right? And then you are also guided by your desire for parsimony or mathematical elegance. And sometimes, and very often actually, I would say, that leads to formulations which are very narrow. So in my talk, I went on this rant about like continual learning, this lifelong learning. It's got this very simple abstraction in the form of, for catastrophic forgetting of examples. Whereas we really want to have a much richer notion of lifelong learning. But that's not what people do in machine learning, and we need to shake them out of it. So I think meetings like this are very good for shaking people out of their comfort zone. And most machine learning or computer vision researchers, they don't want to deal with the complexity of the literature, right? They were not going to spend a lot of time reading through articles and so forth. If they have this little abstraction that they can run with, they'll be happy enough to do that. I think the people in this call are probably the exceptions to that phenomena, but
but I think you're exactly right, and I feel like I was guilty of that before. Or it's an aesthetic choice, really. Like I think a lot of people, they get into machine learning looking for what Pedro Domingos called the master algorithm, right? But I think what many of us learn is that there isn't a single master algorithm, just like there isn't a single loss function, or that quest for some kind of very simple mathematical elegance or one unifying principle isn't necessarily going to be our friend here, right?
We have a recurring question in the from the audience that I was thinking that Bruno might help give some insight on, of this idea of nature versus nurture in the design of an intelligent system. So I'm wondering if you can talk about how important it is, how important the structure of, let's say, a neural network is to the success of an agent compared to learning the weights, so to speak, while it's learned during the agent's lifetime.
Yeah, I think I'm hugely on the side of structure. So, I mean, a lot of these computations and problems that we want to solve, they have a particular mathematical structure. And I think this was the way the field originally started out. And computer vision, I think, was more from an engineering or mathematical angle. And then this learning approach kind of took over, which is great. I mean, everything should be adaptive. But at the same time, I think what we lost from that is a lot of the structure. So you can train these systems to solve these problems, but then you're left with this question at the end of the day, well, what's it doing? And it also, I think, from the point of view of from neuroscience, we're actually looking for insight into the mechanisms. And so, that there is a really big, deep neural network that solves these problems, we already know. So what we want to know is the underlying principles behind that network and how it's working and the structure behind it, right? So, I'm convinced there's all kinds of very advanced and amazing mathematics being implemented there. And so what I want to know is, what is that? What is that structure that's there in the brain? It's not just a perceptron with a lot of weights. So I think that's, it kind of maybe depends what kinds of problem you're trying to solve as well.
Oh, you also mentioned that there may be a need to redesign our neural networks so that they have a more, I think you were calling it a distributed memory system, where every neuron has some memory of what it's seen, and not sure if that memory is some kind of set of exemplars or if it's implicitly encoded in the weights. But can you talk about what you feel would be a good representation for memories?
In an artificial neural networks, I don't know. And I don't think we know neither in the brain. It's just that research in neuroscience on various species, could be animals or human, tend to show that when something is likely to be memorable before even entering in the region that encode memory, which are the hippocampus, there's a lot of activity all over the brain in the region that are related to the object or the scene or the type of activity that are in this event, as well as some part of the language, the region related to language are even activated. And this is before this event is even going to go into memory. So it seems to be that during the feed-forward way or the processing, not all event image are treated the same way. Some are stronger, some are weaker to begin with, and the stronger one, in a way, will make it to memory more often. So then there is this hint that a coding of memorability or memory is very distributed at all the level of a brain, a natural brain. So then, is there a way to do that into artificial neural networks? I will not know how. It is just an insight that I'm taking from neuroscience.
This issue of memorability and its impact on learning is maybe connected to what Dan was talking about in terms of vocabulary taking on different meanings depending on who is saying it to a child, that is. So maybe Dan, can you talk about what, can you make some connection there? Sorry, that's too broad.
I'm not sure I understand maybe precisely what the question is. I think I was talking about, you know, sort of the flexible nature of the meanings of words, right? It's like the problem isn't just to learn a mapping between words, but to know how to use them to do useful things. I think that maybe the broader idea is to think about, you know, humans and by consequence, babies have adapted to solve the problems that humans are trying to solve. And those may or may not be the same problems as the ones that your community is trying to solve. They might be the same to the extent that you're trying to make algorithms and robots that succeed at doing the tasks humans are trying to solve. And otherwise, they might not be. And it's worth, you know, trying to figure out whether things that look like bugs in infants are features for solving general problems or human-specific problems, or kind of more broadly of thinking about, like Liz was saying, the kind of social context in which infants are embedded is super important for letting them, you know, stick around and learn from other people who have lots of representations that they can't themselves represent yet. And so, you know, it's about kind of a flexibility. I guess. I'm not sure I answered your question, but maybe I'm not quite sure I understood the question either. So hopefully I said something interesting nonetheless.
Yeah, I don't think my question made any sense, but that was a great answer anyways.
Okay, do we still have time, or are we going to wrap up? I actually want to ask Dan one question. So so you talk about how parents communicate with their kids will be affected by how the kids have developed it. Like if the kid is smart, then you talk in a smart way. If the kid still don't know anything, you adjust the way you talk. I just wondering if that is also the case for machines. Like we're all talking about how to build like a smart machine, but maybe we should come up with a new field that has like machine psychologists, like people who understand what the machine can do, can understand, and then teach them the best lesson.
Isn't that iterative learning?
Oh, but iterative learning, I think is a little bit different because you are the person and you are going to provide the machine the data or the lessons. So you need to kind of understand what is the most suitable lessons up to this point. I'm not sure. Maybe you can have some comments on this.
It's a good question. I mean, I guess, you know, a couple things that come to mind. There's this idea from people who study design find that if you come to people with really early prototypes that are kind of mocked up by hand, people are really willing to give you lots of comments and change them in radical ways. And if you come to people with a prototype, even if it's a garbage prototype that looks like it's really well done, people are really hesitant about, you know, making suggestions about it. So there might be a sense in which if you build, say, a computer vision system that's very good at recognizing, you know, maybe like Linda was saying, solving some particular narrow kind of problem, other people might be less willing to come along and say, hey, you're solving a you know, irrelevant problem really well. And so, you know, there might be some merit in trying not to get, too ahead of ourselves in coming up with really clever ways of solving uninteresting problems. I would say, just quickly, something that really changed the way that I think about the relationship between kind of cognitive development and machine learning is I went to this workshop years ago called Babies in the Wild that Mike Goldstein put on Cornell, that was talks by cognitive development folks and then commentary by roboticists. And there was a talk by this guy, Brian Scassolotti, who's a roboticist at Yale. And the thing he said that stuck with me was, the thing that cognitive development people should learn from robotics isn't the kind of clever algorithms that they develop. It's like, how much work you need to do to get the system off the ground at all. Like that's way orders of magnitude more important than what learning algorithm you stick in the machine once you come up with a setting where any learning can happen at all. And so maybe that's a related idea that it's worth thinking about what the real problem is before you kind of go too far on solving some facsimile to that problem. And for what it's worth, that's a problem we psychologists have too. I can't tell you how many tasks I've designed in the lab and then spent years caring about that, several years later, I think are irrelevant and wish I hadn't spent so much time. So it's not just you, it's us too. But maybe it's worth not getting over smart about things that maybe you don't need to get over smart about.
Okay, great. So we're about 7 minutes over time. To not keep anyone past their bedtime, let's call it a day here. Thanks very much, everyone, for coming. Especially thank you to all the speakers. Let's, in the audience, give a virtual clap.
I can never forget how to do this.
Thanks to all the organizers for putting together a great workshop, and to all the other speakers for their participation too. It was great.
Thank you to the organizers, indeed.
Yes, very much.
Thank you all for coming. Like, it's our great honor to host you guys here.
Yeah, well, thank you in particular to the student organizers,
Yes.
them and Maria.
Yeah.
You've done so much work. Thanks.
Yeah, thanks everyone, panelists, student organizers. I thought it was really fun.
And making the transition to doing this all online too, which is
Yeah.
we can give you extra great credit for that.
Thank you, everyone.
Okay, bye.
Bye.
Good night.
Bye, everyone. Good night.
Bye.